3.5 million pages, 2,000 videos, 180,000 images. That is the massive pile of data you are looking at in the Epstein files case, and the assumption most people make is simple. You just plug Copilot in and it works. But in reality, it doesn't. Not without the right architecture underneath it. This episode is about the technical infrastructure that actually makes this happen, focusing on the engineering that turns millions of pages into something you can search, reason over, and cite with total accuracy. We are not talking about theory or marketing hype today. We are talking about a working system. By the end of this, you will understand why standard retrieval breaks when you hit massive scale, and you will see how to handle chunking and routing when the noise starts to drown out the signal. We are going to look at what orchestration looks like in practice and how you can actually measure if any of it is working. If you want deep technical insights on Microsoft 365, Copilot, Azure, and the modern workplace, make sure to subscribe to the M365 FM podcast. The data blindness problem. Most organizations think Copilot is just a search tool, but that is not the case. It is an orchestration engine, and when you are dealing with 3.5 million pages, that distinction becomes everything. Here is what happens when you connect Copilot to massive data without a retrieval architecture. The noise-to-signal ratio becomes impossible to manage because Copilot fires a keyword search across millions of documents the moment you ask a question. It returns results where some are relevant and many are not, forcing the LLM to try and find a signal inside a fire hose of candidates. The real answer just gets buried under a pile of half-relevant noise. This is what I call data blindness. The data is not missing, but it is everywhere at once, which ends up being the exact same thing. If you use fixed-size chunking at 512 tokens, you are going to break your legal narratives. Imagine a deposition that spans several pages as one continuous argument, but your chunking algorithm has no way of knowing that. It splits the text right at the token boundary in the middle of a testimony, and the next chunk ends up being someone else's statement from a completely different page. When vector search pulls just one of those chunks, the context is broken, and the answer Copilot gives you is incomplete. Vector search by itself will return irrelevant candidates because your data is too diverse. You have legal documents, emails, transcripts, and photographs with metadata all sitting in the same vector space. When a user asks about a timeline, the vector search might pull images that were tagged with dates close to the prompt in the embedding space. The image had nothing to do with the timeline, but it was semantically close, so Copilot grounds its answer on the wrong data. Then you hit the latency wall. You simply cannot query 3.5 million pages in real time the same way you would query 10,000. Every single stage adds up, from embedding the query and searching the index to re-ranking candidates and passing context to the LLM. Response time starts stretching into seconds instead of milliseconds, and for an enterprise assistant, those extra seconds feel like a total failure. Permission-aware retrieval also becomes a nightmare without proper governance. At this scale, different users have different access rights, where one analyst sees one branch and another sees something else. If your retrieval layer is not trimming permissions at the exact moment of the query, someone is eventually going to see something they should not. You have to bake that permission logic into every single retrieval path and ranking function. Finally, you have the problem of dark data. Most of those 3.5 million pages are completely unsearchable unless you process them first. Scanned PDFs need OCR, videos need transcripts, and images need descriptions, but you cannot do this while the user is waiting for an answer. It has to happen asynchronously during ingestion before the data ever reaches your indexes. If you skip that step, those documents stay dark, meaning they exist in your system, but Copilot is effectively blind to them. Why standard RAG collapses at scale? The research is clear. Semantic chunking sounds great in a white paper, but when you hit 3.5 million pages, the cost becomes a wall. Here is the technical reality. Semantic chunking requires you to embed every single sentence in your corpus, then compute similarity matrices across every adjacent pair just to find where a topic ends. At 3.5 million pages, you are looking at tens of millions of sentences. Every one of them gets embedded. Then you have to run cosine similarity across that entire set to detect where the topics shift. Only after that work is done do you group those sentences into chunks and embed the chunks themselves for the final index. It is effectively a double embedding pipeline that burns through your budget before the data even reaches a vector database. The benchmark data is stark. Fixed-size recursive chunking at 512 tokens hits 69% accuracy on document-level retrieval tasks. Semantic chunking on that same benchmark scores 54%. That is a 15-point gap in the wrong direction. Because the semantic chunks average only 43 tokens, they are so over-fragmented that your retrieval becomes scattered. You lose the context, you lose the coherence, but the real cost isn't just the loss in accuracy, it is the compute. Semantic chunking adds 1.5 to 3 times the ingestion overhead compared to a standard fixed-size split. You are paying for sentence segmentation, embedding infrastructure, and similarity calculations that don't actually improve your end result. On a 3.5 million page corpus, that multiplier turns into weeks of pre-processing time and massive infrastructure bills. You are embedding the same text multiple times, once for boundary detection and again for the final chunks, which is just redundant work at scale. Fixed-size chunking is linear. You tokenize once, cut at intervals, and embed once. It scales predictably. Semantic chunking scales much worse because every single document triggers expensive NLP operations. If you are ingesting 3.5 million pages one time, the delay is annoying. But if you are ingesting data continuously, with new evidence arriving weekly and video transcripts monthly, that semantic pre-processing becomes a permanent bottleneck in your system. Retrieval latency grows right along with your corpus size unless you architect your way around it. With semantic chunking, you have increased your chunk count through overfragmentation, and that increases the total number of vectors in your index. More vectors mean the search has to evaluate more candidates. Your latency on queries starts to creep up, which means you respond slower and your users wait longer. Then you hit the constraint of the LLM context window. You cannot just send all 3.5 million pages to the model. Your window is finite, whether it is 4,000 tokens or 128,000 at the high end. Retrieval has to return a small, precise set of candidates. If your chunking strategy produces tiny fragments, you have to retrieve more of them just to reconstruct the basic context. More retrieved chunks mean more tokens are consumed by the retrieval process instead of the actual reasoning. Your model spends its tokens trying to rebuild a narrative instead of synthesizing an insight. The paradox surfaces right here. More data without orchestration does not lead to better answers. It leads to worse ones. You retrieve more candidates, but they are more fragmented. The LLM receives a scatter of context instead of a coherent story. It starts to hallucinate more because it is forced to piece together statements from disconnected chunks. Users see answers that look like they are grounded in documents, but that grounding is fragile. One chunk says X, and another chunk that is nearby in the vector space but logically unrelated says Y. The LLM then synthesizes a false inference to connect them. Standard RAG assumes you have a small, simple corpus. Maybe some legal documents or product FAQs. At 3.5 million pages with 2,000 videos and 180,000 images, those assumptions break. The default architecture of one chunking strategy and one vector index collapses under that weight. You have to architect differently. You have to be selective about where you invest your resources. The selective activation model. The insight that changes everything is this. Not every document in your 3.5 million page corpus has the same value. Some documents answer 80% of your user questions while others answer none. Your budget is finite, your embedding costs are finite, your latency budget is finite, you have to choose where to invest. This is selective activation. The Epstein files implementation uses a 3-tier architecture. Think of it as a graduated investment where each tier gets exactly the level of sophistication its use justifies. Tier 1 is your high-value, high-frequency content. This includes depositions, legal filings, and testimony from key figures. These documents generate the vast majority of your answerable queries. They are the nucleus of the entire knowledge base. Tier 1 gets the full treatment. These documents are chunked recursively to respect section boundaries and maintain narrative flow. Metadata is extracted at a very granular level to track who testifies and what topics appear. Chunks are embedded with a high-quality model, and results are re-ranked using a cross-encoder. Query time latency matters less here than answer quality because users expect deep, accurate results. If you need a complex answer about a person's movements across multiple documents, Tier 1 retrieval will surface that evidence. Tier 2 is your bulk evidence. This is the supporting material like emails, financial records, and video transcripts. These are secondary sources that provide context but rarely answer a question on their own. Tier 2 uses keyword-only indexing like BM25 and exact match search. There are no embeddings and no re-ranking. This trade-off is a deliberate choice. If a user searches for a specific transaction date, keyword search finds it instantly. There is no embedding overhead and no model latency. You sacrifice the ability to find documents through conceptual similarity, but you gain massive speed and operational simplicity. Tier 2 is perfect for narrow questions like finding all emails from a specific person in March. Tier 3 is the deep archive. This is for historical documents and duplicate evidence that you keep for compliance, but rarely ever query. Tier 3 stays in cold storage. These documents never even enter your hot indexes. If a user query indicates that Tier 3 might actually have something relevant, the system triggers an on-demand extraction. This is expensive per query, but it is acceptable because those queries are so rare. Maybe once a month, a user asks something specific enough to justify a cold storage search. You pay the latency cost then, but the rest of the time, you aren't paying to keep those documents active. The cost picture changes completely under this model. You aren't embedding 3.5 million pages anymore. You are only embedding Tier 1, which might be 500,000 high-value documents. You are running keyword indexing on Tier 2, which costs a fraction of what embedding does. Tier 3 is left untouched. Your embedding budget is suddenly 5 to 10 times smaller. Your vector database is 5 to 10 times smaller. Your query costs drop because the system routes the request to the right tier based on what the user is asking. This approach requires real governance. You need a framework to decide which documents land in which tier. When you ingest data, you have to classify it immediately. A key deposition goes to Tier 1, while a supporting email goes to Tier 2. This can be done with simple rules or metadata. For example, documents older than 5 years that are marked as archived can go straight to Tier 3. Your measurement of success becomes the cost per answerable query rather than just the raw document count. You track how many queries Tier 1 answers and how often you need to pull from Tier 2. If you find that financial records are answering 40% of your queries, but you have them in Tier 2, you move them up to Tier 1. You are constantly optimizing where you spend your infrastructure budget. The business case here is very straightforward. Not all data is equal, so you shouldn't treat it like it is. Recursive structure-aware chunking. Once you've decided what goes into each tier, you hit the second big decision, how to actually split your documents into chunks. This is where most projects fall apart. People choose a strategy because it sounds good on paper, but then they realize it doesn't work for the content they actually have. Legal documents aren't just walls of text. They have a specific structure with articles, sections, and numbered provisions that isn't there by accident. That structure encodes the actual meaning of the document. An article usually contains a complete legal concept, while a section inside that article refines the idea and a subsection clarifies a tiny detail. When you split these documents up, you have to respect that hierarchy instead of just cutting through it. The recursive structure-aware approach starts with one simple rule. Use the document's own structure as your primary signal. Don't just count tokens and cut. You need to build a hierarchy. The logic here is pretty straightforward. You take a document and start at the highest level, like an article. If that entire article fits into your token budget, you keep it as one single chunk. But if that article is too big, let's say it's over 512 tokens, you move down to the next level. You split the article into sections and try to keep those as chunks. If a section is still too large, you go deeper into paragraphs or even sentences. You only force a split based on token counts after you've tried every possible structural boundary. You keep refining until every piece fits within your limit. Why go through all this trouble? It's because legal meaning lives at these specific boundaries. An article makes a full argument, and a section advances that point. So respecting these divisions keeps the narrative together. The context stays in one piece. When Copilot pulls a chunk about termination conditions, it gets the entire list of rules instead of a fragment that was cut off in the middle of a sentence. The extra work here is actually minimal compared to more complex semantic methods. You aren't calculating embeddings for every single sentence just to find where a topic changes, and you aren't running math across millions of pairs. You simply pass the document structure once when you bring it into the system. Most PDFs and Office files already have this structure built in through headings and tags, so you just use a standard library to pull it out. The parser runs once and you're done. Overlap is how you bridge the gaps on purpose. Even though recursive chunking aligns with meaning, every boundary carries a risk that important context might get split between two pieces. You fix this by adding a 10 to 15% overlap, which is usually about 50 to 100 tokens. When you chunk at the section level, you take the last few sentences of one chunk and repeat them at the start of the next one. If a user's question hits that boundary, the system pulls both chunks and the information flows without a break. Metadata needs to travel with every chunk you extract. When you split a document at the section level, you should pull the article number, the title, and the effective date at the same time. This data stays attached to the chunk forever. During a search, you can filter by specific articles or look within certain date ranges to make sure the answer is still valid. Metadata becomes a way to rank results, so an older section might carry less weight than a newer one. The numbers back this up. Testing shows that recursive chunking at 512 tokens hits 69% accuracy on legal retrieval benchmarks. That is just as good as expensive semantic methods, but without all the processing lag. We use 512 tokens as a target because it balances keeping enough context with staying precise. If chunks are too small, the story breaks, but if they're too big, the specific answer gets lost in the noise. The actual setup is very practical. You pass the structure, chunk it recursively, and pull the metadata. Then you embed the chunks once and start testing with real questions. You look at the results, tweak your thresholds, and move it into production. The overhead is low because the structure is already there. You aren't inventing anything new. You're just finally respecting the way the document was written. The multimodal ingestion pipeline. You might have 2,000 videos and 180,000 images buried in a 3.5 million page collection. Copilot cannot watch those videos in real time, and it definitely can't interpret raw pixels while a user is waiting for an answer. If you tried to send raw image data to an AI during a search, you would hit your limit and destroy your speed within the first few seconds. You have to make this media searchable before anyone ever asks a question. This happens through a process called asynchronous enrichment. The system runs in the background during off-peak hours to turn images and video into text that the computer can actually understand. It starts with your scanned documents. A huge portion of those millions of pages are probably physical evidence, photos of files, or handwritten notes. These aren't digital text, they are just pictures of words. You use OCR, optical character recognition to turn those images into text during the ingestion phase. You feed the PDF to the engine, extract the words, and then chunk that text using the same structural strategy we just talked about. We also attach metadata about who scanned it and where it came from. If the OCR isn't sure about a word, it flags it with a confidence score. If a user gets an answer based on a messy scan with 70% confidence, they'll see that in the citation so they know to double-check the original. Videos need to be transcribed next. You might have thousands of videos or hours of testimony to get through. If you try to transcribe a video the moment a user asked a question, the system would be way too slow to use. Instead, you do it ahead of time. You send the audio to a speech-to-text service to get a full transcript and a quick summary. If you can identify who is speaking, you label those segments too. That transcript becomes the part the AI actually searches. We keep the timestamps as metadata, so when a match is found, the system doesn't just show text. It says, see the testimony starting at 1:24:30, and gives the user a link to jump right to that spot. Images require a different kind of processing. Running a massive vision model on nearly 200,000 images is expensive and slow. To solve this, you use a smaller, faster model that is built for speed rather than perfect artistic detail. You give the model a simple job: describe what you see, find any text, and list the people or objects in the frame. The model gives you a text description, and any visible words are pulled out via OCR. This text becomes the metadata for the image. When Copilot finds a match, it isn't looking at the pixels, it's reading the description of those pixels. Metadata enrichment has to happen across every single format. We use named entity recognition to find people, places, and dates in every document and transcript. We also look for relationships, like seeing that person A and person B were in the same room on a specific date. If a user wants to know what happened in 2005, the metadata filters the search down to only the files tagged with that year. This all happens once during the initial setup, not every time someone types a query. Your storage strategy should separate the hot and cold data. The original heavy files like PDFs and videos stay in cheap storage where they are rarely touched. The extracted text and metadata live in fast indexed databases that the AI can search instantly. When a search happens, the system pulls from the fast index. If the user actually needs to see the original photo, they just click a link to the cheap storage. This keeps the AI from getting bogged down by massive files it doesn't need to see. All of this work, the OCR, the transcription, and the vision processing, happens on a schedule. It might run every night or every week as new documents arrive. The enrichment finishes before the data ever hits the search index. This is why the user gets an answer in seconds. All the hard, expensive work was already finished before they even opened the app. This is the only way to handle massive amounts of different media. You make it searchable without breaking your budget or making your users wait forever for a response. Entity extraction and knowledge graphs. Raw text is noise, but structured entities are signal. By this stage in your pipeline, you have already chunked your documents and enriched your media, but you still face a massive retrieval problem. Imagine a user asks about the relationship between person X and person Y. Your chunking strategy might pull up relevant passages, and your embedding model will find semantically similar text, but the final answer still forces the LLM to do the heavy lifting. It has to read through disconnected statements across multiple chunks and try to synthesize a relationship on the fly. If those statements come from different indexes or different time periods, the connection weakens, and the LLM starts to infer. At scale, inference turns into hallucination. You need a layer that extracts these relationships before the query ever arrives, and that layer is entity extraction and knowledge graphs. Named entity recognition runs during the enrichment phase, where every document, transcript, and image description passes through an NER model. This model identifies every person, organization, location, and date mentioned in your text. It sees that person X appears in document A on page 42, while organization Y shows up in the contract section of document B. The system extracts these with precise position information, so it doesn't just note that a person exists in your data. It records that person X was mentioned at exactly 12 minutes and 56 seconds into video 3. Relationship mapping then takes these isolated extractions and turns them into a graph that captures real-world connections. If person X appears with person Y in one document and wires money to organization Z in another, the graph maps that path. While none of these facts are remarkable on their own, they form a clear pattern when viewed together. The graph itself does not interpret the pattern, as that is the LLM's job during generation, but it surfaces the structure so the LLM doesn't have to scan and guess. Cross-reference resolution is how you solve the identity problem across millions of pages. Person X might be mentioned hundreds of times, but the text won't always use their full name. Sometimes the data says Mr. X. Sometimes it just uses a last name, and other times it uses a pronoun like he or she, depending on the context. You have to recognize that all of these mentions refer to the same individual, which requires fuzzy matching at scale. By using string similarity and co-occurrence patterns, the system links these mentions to a single canonical identifier so your data stays clean. Temporal indexing is what organizes your graph by time because entities are never static. A person's role changes, their association with a company ends on a specific date, and their involvement in an event spans a specific range. Your graph stores this metadata, allowing a user to ask what changed about a person's role after a certain date. Because this information is indexed, these queries are answered at the retrieval stage rather than forcing the LLM to hunt for dates in free text. Confidence scoring is used to mark uncertainty because not every extraction is a guarantee. The NER model might find a name with 98% confidence in one sentence, but only 62% confidence when it's guessing based on a pronoun. The system records these scores so the user knows if an answer is grounded in solid facts or uncertain inferences. This level of transparency is what prevents the system from showing false confidence when the data is thin. Query leverage fundamentally changes how people interact with your information. Instead of basic keyword searches for a name, users can search by the entity itself to see every document where that person appears. They can ask for a list of every location a person visited in 2005 or define the relationship between two specific parties. These entity-based queries are more precise and align with how people actually think about their data. The implementation handles all of this during ingestion so that queries run fast when it matters. You build the graphs, index the relationships, and attach the temporal metadata once. The result is a system where users get answers grounded in structured relationships rather than loose textual associations that might lead to errors. The Agentic router, query decomposition. You have invested heavily in your data architecture at this point. Your documents are chunked across 3 tiers, your images have descriptions, and your knowledge graph tracks every relationship and date. Everything is ready for use, but this is where most systems fail. A user asks a question and the system has no idea how to interpret the intent or which layer of the architecture it should actually trigger. A standard retrieval pipeline treats every query exactly the same way by searching vectors and returning results. This works fine for simple questions, but enterprise data is rarely that straightforward. If a user asks for flight logs from 2005 regarding a specific person, a simple semantic search will likely fail. That request requires the system to understand a specific time, a specific entity, and a specific type of record. You cannot rely on a single retrieval path, so you need an agent that breaks the question down and routes the pieces to the right systems. This is the role of the agentic router. Intent classification is the very first decision the router makes. When a query comes in, the system classifies what the user is actually looking for, whether it is a temporal, relational, or transactional request. It might be a structural query about how documents are organized or a simple entity search. To keep things fast, you should use a lightweight supervised classifier rather than an expensive LLM call. This classifier runs in just a few milliseconds and provides an intent type along with a confidence score to guide the next step. Subquery generation then breaks the main question into smaller, discrete tasks that match the identified intent. If a user asks for flight logs from 2005 for person X, the router sees this as a mix of temporal, entity, and structured data needs. It generates 3 separate subqueries, one for the knowledge graph, one for the SQL database, and one for the document index. Each of these is written in the specific syntax that the target system requires. The router then fires all 3 requests in parallel while maintaining the relationship between them. Data silo routing determines which specific index each of those subqueries should hit. Your architecture likely has multiple systems, including SQL databases for records and vector indexes for concepts. The router keeps track of what each system contains, so it can send a transaction query to the database and a conceptual query to the vector index. While this routing can be learned through feedback over time, it usually starts with a set of rules that connect intent classes to the most logical data source. Result synthesis is the process of merging all those different answers before the LLM ever sees them. Because different systems respond at different speeds, the router collects the results asynchronously and checks for redundancy. If the knowledge graph and the document search both confirm the same connection, the router weights that finding more heavily. It also looks for contradictions between sources and flags them immediately. By the time the LLM receives the data, it is looking at a cross-checked set of candidates, which significantly drops the risk of hallucination. Fallback logic ensures the system handles failures gracefully without giving up on the user. If a database search for a specific person comes up empty, the router doesn't just stop. It automatically tries an alternative path, like searching the document index for that same person and date. These pre-planned fallback routes happen behind the scenes, so the user sees a complete answer instead of an error message. It turns a potential failure into a successful retrieval by checking every available resource. Confidence thresholds are used to decide when a query needs to be escalated. If every subquery returns a low confidence result, or the fallback paths fail, the router flags the entire request as uncertain. Instead of letting the LLM guess and potentially lie, the system can trigger a search of cold storage or ask the user for clarification. It might even escalate the task to a human analyst for review. This prevents the system from projecting false certainty when the data just isn't there. The agent itself is designed to be lean, fast, and strictly rule-based to keep latency at a minimum. Its only job is to figure out what the user wants and orchestrate the retrieval process efficiently. By letting each specialized system do what it does best, the router ensures that the final answer is as accurate as possible. Hybrid retrieval strategy. The router has made its decision, and subqueries are now firing across different systems. Now, those systems need to return candidates that are both precise and semantically relevant. This is where the hybrid approach becomes essential. Think of your retrieval layer as having two parallel search mechanisms running at the same time, and each one has its own distinct strengths. BM25 is the probabilistic keyword search algorithm that has been the industry standard since the 90s, and it excels at precision. If you ask for documents mentioning a person by name, BM25 finds those exact matches instantly. You want records from March of 2005, or specific transaction amounts, or precise legal terminology, BM25 owns these. It is deterministic and fast, but it only works at the surface level. If a document discusses the same concept using different vocabulary, BM25 is going to miss it. Vector search does the opposite work by embedding your query into a semantic space. It finds documents whose embeddings are closest in that space, which allows it to find conceptual similarity across different words. You might ask about financial transfers between parties, and vector search will retrieve documents discussing money movement, even if they use words like payment or disbursement instead of transfer. But here's the problem. Vector search can be noisy. A document that is semantically similar to your query might be totally irrelevant to what you actually need, because embedding space distance does not always align with what a user wants. Combining them yields something neither provides alone. You run BM25 against your corpus to get a ranked list of keyword matches, and simultaneously you run a vector search to get a ranked list of semantic matches. These two lists almost never align perfectly. BM25 puts exact match documents at the top, while vector search scatters results based on semantic proximity. The union of these two lists contains both precision and recall. The intersection contains documents that match both criteria, meaning they are exact matches and they are semantically coherent. But you cannot just stack the results. You have to fuse the rankings. Reciprocal rank fusion handles this. RRF takes the BM25 ranking and the vector ranking and merges them using a formula that avoids favoring one signal over the other. If a document ranks first in BM25 and 10th in vector search, RRF gives it a high weight because it is important to both methods. If a document ranks second in vector search but appears nowhere in BM25, RRF places it lower because semantic similarity without any keyword connection is a weaker signal. The fused ranking reflects where the two methods agree and where they complement each other. In practice, RRF produces better results than either method alone because it balances precision and recall. Metadata filtering happens before or after retrieval depending on your architecture. Before retrieval, you narrow the search space to make things more efficient. If a user query asks about the year 2005, you filter the indexes to only show documents with 2005 dates. This reduces the candidate set before any expensive operations run. After retrieval, you filter results by permission to ensure security. If a user does not have access to a specific document, the system removes it from the results. Metadata filtering at query time is essential for compliance and security, but it does add latency. Pre-filtering is faster because it reduces the total workload, not because the logic is more sophisticated. Re-ranking applies after the hybrid fusion is complete. You have a merged candidate set ranked by RRF, and now you pass this to a cross-encoder model. This is a lightweight transformer that reads the query and each candidate together to assign a new relevance score. The cross-encoder understands query document interaction better than embedding similarity alone, which allows it to catch small nuances. A document that is semantically close but contextually wrong will drop in score, while an exact match document that is slightly off-topic gets reweighted. The re-ranker produces the final ranking, and your top candidates come from this list. The cost of all this is latency. RRF itself is fast because it is just arithmetic on two ranked lists, and metadata filtering is fast because it uses simple comparison logic. But re-ranking hits a neural model, which typically adds 100 to 150 milliseconds for a batch of 50 candidates. That is a meaningful delay. In aggregate, your search call might take 150 to 300 milliseconds instead of the 30 to 50 milliseconds you would see with pure vector search. The payoff is precision. Precision gains compound as you move downstream. Fewer bad candidates reach the LLM, which means fewer tokens are wasted on irrelevant context and there are fewer hallucinations. The marginal latency cost prevents much larger problems later. Permission-aware retrieval. At 3.5 million pages, you cannot afford to surface the wrong document to the wrong person. Governance is not optional. It is the difference between a working system and a massive legal liability. Your retrieval infrastructure is now solid, hybrid search finds candidates, re-ranking orders them, and the LLM grounds the answers. But none of this matters if retrieval returns a document the user is not allowed to see. That is not just a technical failure, that is a security breach. The problem scales as the corpus gets bigger. In a small knowledge base, access control happens at the document level, where a user either has permission or they do not. It is binary and simple. At 3.5 million pages across multiple tiers and silos, permission becomes granular. A user might have access to some sections of a document but not others, or they might see emails from one time period but not another. They can see financial summaries but not the raw transaction details. These fine-grained access patterns cannot be managed at the document level. They need to live at the chunk level. This means access control lists must travel with the data during ingestion. When you chunk a document, you do not just extract the text and embed it, you extract the permission metadata as well. You need to know who created the chunk, which users have read access, and what the classification level is. This metadata attaches to every single chunk. It is not stored in a separate database. It is indexed right alongside the chunk content. During retrieval, the permissions are always available for the system to check. Query time filtering trims the results based on user identity. A user submits a question, and the system identifies them through Azure AD or another identity system. The router passes that identity through the retrieval pipeline. When BM25 returns candidates, the filtering logic immediately removes chunks the user cannot access. The same thing happens with vector search. Re-ranking only receives chunks the user is authorized to see. By the time the results reach the LLM, every candidate has been permission checked. The LLM never sees restricted content, and it only generates answers from documents the user is authorized to access. This filtering adds more latency to the process. You are not just retrieving candidates, you are checking permissions for every single one of them. A re-ranking operation over 50 documents means 50 individual permission checks. Modern systems batch these checks, but permission evaluation is still overhead. Typical query latency increases by 30 to 50 milliseconds. For systems that are sensitive to compliance, that is an acceptable cost. For real-time systems, it is a trade-off you have to accept because leaking access is a much worse outcome. Sensitivity labels are how you express policy. Copilot does not inherently understand that a document marked as legally privileged should have tighter controls than something marked as internal. You encode that understanding into sensitivity label policies. Each label has its own rules. Confidential documents can only be accessed by the legal department, while internal documents are accessible to authenticated users, but not guests. During ingestion, documents get labeled and those labels become metadata. At query time, the filtering logic respects these policies. A user requests a search, the system checks their identity against the label policies, and the results are trimmed. Compliance boundaries add another layer of complexity. In regulated industries, data residency matters quite a bit. Personal information about residents in the EU cannot be processed in US regions, and health information has its own specific access rules. These boundaries are not enforced by Copilot alone. Your retrieval system must enforce them. If a user in the US queries the system, the retrieval must respect US-only data boundaries. If a compliance officer runs a discovery search, the retrieval must respect audit and retention rules. Audit trails log every single action. They track every retrieval, every result shown, and every document accessed through Copilot. This is not for performance monitoring, it is for accountability. If a breach occurs and someone accesses data they should not have seen, the audits show exactly how it happened. You can see which user it was, what they asked, and what documents were returned to them. This logging happens at retrieval time, not generation time. The moment a chunk becomes a candidate, the system logs it. The implementation requires real infrastructure. You need identity and access management, permission metadata stores, and filtering logic at the retrieval stage. You also need audit logging pipelines. This is not a feature you can just bolt on at the end. It is foundational. Without it, your entire retrieval system is a compliance risk. With it, permission-aware retrieval becomes invisible to the users. They see the answers they need, and the system quietly ensures those answers come from data they are authorized to access. Chunking performance benchmarks. Theory is one thing, but real-world performance is where the model actually breaks or holds up. Here is what the research actually shows. The moment you move from architectural design to actual implementation, benchmarks become your only source of truth. They tell you whether your choices were right or if you've built a system that fails under pressure. The question you have to answer is simple. How does your chunking strategy actually perform on the content you're trying to retrieve? We've discussed recursive structure-aware chunking as the go-to approach for Tier 1 and Tier 2 content. This isn't just a theoretical preference or a hunch. The benchmark validation is important because it proves that this method is grounded in measured, repeatable performance. When you look at the data, fixed 512 token recursive chunking achieves 69% accuracy on document-level retrieval tasks. That is your baseline. If you ask 10 questions, recursive chunking finds the document containing the answer 9 times out of 10. The beauty of this method is that the chunking is clean. It respects section boundaries and preserves context, which means it maintains narrative continuity instead of shredding the document. When you ask about a specific legal provision, the retrieval process finds that section intact rather than giving you a fragmented mess. Compare that to semantic chunking on the same corpus. Semantic chunking scores 54% accuracy, which is 15 percentage points lower than the recursive method. But the hidden cost is even more revealing. Semantic chunking produces chunks averaging only 43 tokens, and that is far too small for most enterprise needs. It's over-segmented because the boundary detection algorithm splits the text whenever semantic similarity drops even slightly. A new topic starts, so it creates a new chunk. A new speaker joins the dialogue, so it creates another new chunk. The result is a pile of small pieces instead of coherent units, forcing the system to pull multiple fragments just to reconstruct basic context. Your LLM receives scattered evidence instead of a continuous narrative. The latency consequence is direct and painful. More chunks mean more vector database operations, and more retrieval candidates mean more re-ranking candidates to process. A query that takes 30 milliseconds with recursive chunking might take 120 milliseconds with semantic chunking because the index is larger and the candidate set is bigger. When you spread this across thousands of queries, the cumulative difference is substantial enough to slow down the entire organization. Overlap impact gives us another lever to pull. The benchmark tested overlap at 0 and then at different percentages to see what changed. A chunking strategy with 0 overlap, where consecutive chunks are completely disjoint, yielded only baseline precision. However, adding a 64-token overlap, which is about 10% at 500 token targets, increased precision by 14.5%. That is a massive jump for a small change. Overlap prevents boundary loss because important context near a chunk edge might be missed if it falls just outside the window. With overlap, that context appears in 2 chunks, so if the query matches the boundary, you retrieve both and keep the context continuous. The cost is minimal since it only increases the chunk count slightly, and the precision gain more than justifies the extra tokens. One of the most crucial findings is that embedding quality matters more than chunking strategy when you're using models like GPT-4. You might assume that finding the perfect chunking strategy is the bottleneck, but in reality, it isn't. If your embedding model is weak, even perfect chunks will produce mediocre vectors that the system can't use effectively. If your embedding model is strong, the differences between chunking methods start to compress. A strong model can extract relevant signals from imperfect chunks, whereas a weaker chunk boundary is only a major problem when your retriever is also weak. This inverts how we usually think about precision. Don't waste time over-optimizing chunk boundaries if you're using powerful embedding models, and instead invest that energy into the embedder itself. Cost comparison across these strategies shows the pragmatic trade-off you have to make. Semantic chunking adds 1.5 to 3 times more pre-processing overhead compared to fixed recursive chunking. That multiplier compounds quickly across 3.5 million pages, and you aren't just paying that fee once. You're paying that multiple across the entire ingestion pipeline every time data changes. For environments where you ingest data continuously, semantic pre-processing becomes a permanent bottleneck that slows everything down. For one-time ingestion, the cost is concentrated, but it's still a significant hit to the budget. The practical recommendation from these benchmarks is straightforward. Start with fixed recursive chunking at 512 tokens with 10 to 15% overlap. Test that on your actual content and measure the retrieval precision and answer quality before changing anything. Only if you see clear failure modes, like consistent retrieval failures on a specific question type, should you layer on semantic refinement. Don't assume semantic is better just because it sounds more advanced. Measure the results and then decide. Latency and time to first token, TTFT. Speed matters, and at a scale of 3.5 million pages, latency compounds until it breaks the user experience. You have to architect for speed from day one. Let's be concrete about what latency actually means in a system like this. Time to first token, or TTFT, is the gap between a user hitting enter and the first word of the answer appearing on the screen. It is the only thing the user cares about when it comes to responsiveness. For a search interface, a sub-second TTFT feels instant, but 2 seconds feels slow, and 5 seconds feels completely broken. At enterprise scale, TTFT is the difference between a tool people actually use and a tool they learn to avoid. Your retrieval pipeline has many stages, and every single one of them consumes precious time. It starts with keyword search. BM25 against a well-indexed corpus usually runs in 10 to 50 milliseconds depending on how complex the query is. A simple exact match query might hit the low end, while a complex Boolean query might hit the high end, but this stage is rarely the bottleneck. Vector search also completes in tens of milliseconds for optimized indices when running in parallel. When you run both simultaneously through hybrid retrieval, neither blocks the other, and the first one to return simply feeds the results forward. Re-ranking is where the latency really starts to accumulate. The cross-encoder model is a transformer that has to read the query and the candidate together to evaluate them. Re-ranking 50 documents at typical lengths takes roughly 100 to 150 milliseconds. That is a meaningful delay because it's 3 to 5 times slower than the initial retrieval. You're trading speed for precision here, and the decision to re-rank is purely architectural. Some systems skip it for applications where speed is everything, but others always include it because the precision gain prevents the LLM from hallucinating. For enterprise knowledge assistants, the 150 millisecond cost is usually acceptable because sending noisy candidates to the LLM creates much worse problems later on. Permission filtering adds even more latency to the re-ranking stage. Each candidate requires an access check to make sure the user is allowed to see it. You can mitigate this with batch operations by collecting 50 candidates and checking them all in a single authorization call. It's still overhead though, and 30 to 50 milliseconds for permission evaluation is normal for a full candidate set. Then you have context shaping. Once the top candidates come back from retrieval, those raw chunks need to be assembled into a coherent context for the LLM. You might deduplicate the results if two chunks say the same thing, or you might expand the context to include surrounding sentences for better continuity. You might even order the results by date or relevance to make them more readable. This assembly process is fast and usually stays under 50 milliseconds, but it's still a cost you have to account for. The LLM call is the dominant stage of the entire process. Generating an answer from the context takes anywhere from 200 to 800 milliseconds depending on the model size and how long the answer is. A small model generating 100 tokens might take 200 milliseconds, but a large model generating 500 tokens will likely take 800. This is where most of your TTFT budget is spent. If you reduce the context you send to the LLM, you reduce the generation time, which is another reason why re-ranking is so important. Fewer, higher quality candidates mean shorter context, and shorter context means faster generation. Your total TTFT budget is typically between 500 and 1000 milliseconds for enterprise assistance. Anything under a second feels responsive to a human, but once you go beyond 2 seconds, users start getting impatient and lose focus. Caching is the best way to eliminate most of this latency for repeat queries. If a user asks the same question twice, you shouldn't be recomputing embeddings or rerunning retrieval. You should cache the answer from the first query and return it instantly. For knowledge bases with common questions, caching absorbs a huge fraction of your traffic. A financial assistant might answer a question about a specific policy 50 times a month, so you should cache that answer after the first request. Every subsequent request will get that response in milliseconds instead of seconds. Parallel processing is how you hide latency under concurrent execution. While the initial retrieval is running, you can begin the embedding processing for the next step. While re-ranking is happening, you can start constructing the LLM prompt. Modern systems don't wait for one stage to finish before starting the next, and instead, they pipeline the operations. The elapsed time is the critical path through the pipeline rather than the sum of every single stage. A system where retrieval, permission checking, and re-ranking run in a sequence might take 300 milliseconds, but that same system with parallel execution might only take 150 milliseconds because the operations overlap. The architectural lesson here is very straightforward. TTFT is a design constraint that drives every other decision you make. It drives chunking decisions because smaller chunks retrieve faster, and it drives re-ranking choices because lighter models trade precision for speed. It even drives your caching strategy by forcing you to decide which queries are worth pre-computing. When you're dealing with 3.5 million pages, you're making these choices constantly. If you get them right, users get a responsive system, but if you get them wrong, even the most perfect answers will feel too slow to be useful. Metadata enrichment and its impact. Research into retrieval systems shows us something that feels completely wrong at first, and that is the fact that metadata often matters more than your actual chunking strategy. You might have spent a fortune on your retrieval architecture by setting up recursive chunking, hybrid search, and complex entity graphs. But the data tells a different story because when you add rich metadata to your chunks, your accuracy goes up much faster than it does when you just try to refine your chunking boundaries. A chunk without metadata is just a fragment floating in space, whereas a chunk with proper metadata becomes a searchable object with context, a location, and specific hooks for the system to grab onto. We can actually quantify this accuracy lift in a real way. If you don't use metadata enrichment, your question-answer system is probably going to hit about 50 or 60% accuracy on difficult tasks. Users ask a question, the system finds some candidates, and the LLM tries to build an answer. But the problem is that the LLM has no anchors to hold onto. It has no way of knowing if a document is brand new or 10 years old, and it can't tell the difference between a casual mention and a primary source. Once you add metadata, that same system jumps to 75% accuracy, and that 15% gap is the difference between a tool people hate and one they actually trust. The way this works is actually very simple because the metadata just travels right alongside the content. When you pull a document into the system, you extract structured details like the document type, the creation date, and the specific jurisdiction it belongs to. If you were looking at something like the Epstein files, your metadata would include the name of the person testifying, the case references, and specific topic tags. Every single chunk carries these details with it, which means they become part of the index and stay available every time a user runs a search. When a query happens, metadata serves as both a filter and a way to rank the results. If a user asks about something that happened in 2005, the metadata filter immediately shrinks the search space, so the system only looks at chunks tagged with that specific year. This makes the search much faster because you aren't running expensive operations on files that don't matter. But metadata does more than just filter, it also helps with ranking, because it can tell the difference between a primary source from 2005 and a summary written in 2015 that just happens to mention that year. The quality of your metadata depends entirely on how you extract it. Some of these fields are easy to get because things like creation dates and author names are usually embedded right in the file properties. You can use simple rules to pull that data with high confidence, but other fields require a bit more intelligence to get right. You might need a machine learning classifier to decide if a document is actually about a specific topic or if it just mentions it once. The system then flags which pieces of data are rule-based and which ones are predicted, so the user knows exactly how much they should trust the result. Keeping the system running is a real challenge because metadata is never static. Documents get updated, sensitivity levels change, and old policies expire, which means a file marked as internal today might be public by tomorrow morning. Your enrichment pipeline cannot just stop after the initial ingestion, so you need a scheduled process to review your documents every month or quarter to refresh those tags. If a new version of a file comes out, the old metadata needs to be marked as deprecated immediately. This ongoing maintenance might seem expensive, but it is much better than the alternative, which is having your system return outdated information because the metadata drifted over time. Setting this up does add some overhead to your infrastructure. You have to build the extraction logic, find a place to store the fields in your database, and write the ranking logic for the retrieval step. But this investment pays off on every single query the system handles. Unlike chunking tweaks that only help specific types of questions, metadata enrichment makes the entire system smarter and more reliable for every user. Handling multimodal queries. Users are going to ask questions that point to both documents and videos at the same time. Your system has to be able to handle that without splitting the search into separate buckets that don't talk to each other. The real difficulty here is detecting what the user actually wants. When someone asks a question, the system has to figure out if they need a video, a document, or both. A phrase like "show me what happened in the meeting" is tricky because it could mean the user wants the transcript, the handwritten notes, or the actual video clip of the event. The system cannot guess, so it has to use query understanding to figure out the multimodal intent behind the words. This intent detection happens very early in the process. A lightweight classifier looks at the question and tags it based on what it finds, such as looking for temporal words like "during the meeting" to trigger a transcript search. If the user says "how does it look?", the system flags the query for image or video retrieval instead. These tags aren't exclusive, so a single query can have multiple signals that tell the system to route the search to several different places at once. The embedding challenge goes even deeper than that. Most models only work with text, but your library now includes video transcripts and image descriptions that all have different semantic properties. An image description might say, "two people in a room," while a transcript says, "person A and person B met," and a document might just call it a formal meeting. A standard text model would see these as three different things, even though they are all describing the exact same moment in time. Multimodal embeddings fix this by putting different types of media into one shared space. These models take text, images, and video data and turn them into vectors that you can actually compare against each other. A multimodal model understands that a picture of a meeting and a document about that meeting belong in the same semantic neighborhood. When you embed a user's query, it lands in that same neighborhood, allowing the system to pull candidates from every modality and rank them together in one list. Cross-modal retrieval is what allows the system to find a video that visualizes a concept found in a document. If a user asks about a specific person's involvement in a business deal, the system pulls the contracts, the video of their testimony, and even photos of the checks involved. The user gets a complete picture of the event because they have the textual evidence, the first-hand video, and the visual proof all in one place. To keep things precise, you have to make sure the transcript alignment is perfect. When the system finds a video transcript, it shouldn't just hand over a giant block of text, but should instead preserve the timestamps and speaker names. When a user sees a result, they should see exactly when the person started talking, along with a direct link to that moment in the video. This bridges the gap between searching through text and watching the media, giving the user the speed of a search engine with the context of a film. Visual grounding is the process of returning different types of evidence together. If a user is looking for details on a transaction, the system should show them the financial spreadsheet and a photo of the signed check at the same time. The document gives them the data they need, while the image provides the verification they want. Neither of these is as strong on its own as they are when you present them together. The final step is a fusion strategy that merges all these parallel paths before the final ranking happens. Text, video, and image searches all run at the same time, and then the fusion logic combines the results into one set. You can use reciprocal rank fusion to make sure the modalities are competing fairly against each other. If a result shows up as a strong signal in both the text and the video, it gets boosted to the top of the list, while weaker signals naturally fall toward the bottom. In the end, the system gives the user one unified list of results. They don't have to click through different tabs. for videos and documents because everything is interspersed based on how relevant it is. This allows the LLM to take all that mixed evidence and turn it into a single, coherent answer that is grounded in every piece of data you have. The orchestration layer, putting it together. All these pieces, chunking, routing, retrieval, and re-ranking, have to work together, and that is where the orchestration layer comes in. Think of your architecture not as a bunch of isolated parts, but as an integrated system where every single piece triggers the next one. At the very center of everything sits the orchestration layer, and its only job is to coordinate the flow of information. Data flows in one direction during ingestion, while queries flow in another direction from retrieval to generation. The orchestration layer makes sure that data lands in the right place at the right time, and it ensures that user queries get routed efficiently through the systems you've prepared. The ingestion pipeline works as a sequence, starting when raw documents arrive at the front door. You might have 3.5 million pages, plus videos and images, and they all enter the system as raw bytes. The first stage is extraction, where PDFs are parsed, images go through OCR, and videos are transcribed into text. This extraction happens in parallel, so you don't have to wait for document 1 to finish before you start processing document 2. Extraction runs on a cluster that can process thousands of documents at the same time, and as that work completes, the documents flow into the chunking stage. The chunking process follows the recursive, structure-aware hierarchy we talked about, which produces chunks that actually align with the document architecture. From there, chunks flow into enrichment, where named entity recognition runs and temporal metadata is pulled out. Sensitivity labels are applied to keep things secure, and then the chunks flow into the embedding stage. Your embedding model processes them in batches to produce vectors, and then those vectors and metadata flow into storage. The vector database receives the vectors, the keyword index takes the text, and the knowledge graph receives the entity relationships. Chunks land in specific tiers based on how you've classified their value, and while all of this is happening, audit logs record every single step. Document fingerprints are computed to stop duplicates from getting in, progress is tracked, and any failures are logged so they can be retried automatically. This entire pipeline is asynchronous, which means the different stages don't block each other from moving forward. While extraction is busy processing batch 10, the chunking stage is already working on batch 8, and enrichment is handling batch 6. The pipeline works like a conveyor belt where every stage feeds the next one, and this makes bottlenecks immediately visible to the team. If embedding becomes a constraint, you scale the embedding service, and if storage is slow, you focus on optimizing your writes. The orchestration layer monitors the throughput at every single stage and shows you exactly where the system needs to be improved. The query pipeline is just as sequential, but it also involves a lot of branching logic. A user submits a question, and the system immediately routes it through intent classification to see what they're actually asking. Intent tags trigger different retrieval strategies, and the orchestration layer receives these tags to decide which retrieval systems it needs to call. A query about dates and specific people might trigger the knowledge graph, document search, and metadata filtering all at once. On the other hand, a simple structural query might only need to invoke BM25. These decisions are deterministic based on the intent, so they don't require any human intervention to move forward. Parallel retrieval paths fire off at the same time, and as results come back from each path, the orchestration layer collects them. Results are merged using RRF or another fusion strategy, and then the re-ranker looks at the entire merged candidate set. As soon as re-ranking is done, permission filtering kicks in, and the orchestration layer trims the results based on who the user is and what they're allowed to see. The trimmed results feed into context shaping, where the system assembles the top K candidates into a coherent block of text for the LLM. Redundancy is stripped out, temporal ordering is applied, and narrative continuity is preserved so the model doesn't get confused. The shaped context flows to the LLM, the model generates an answer, and the orchestration layer logs that answer alongside the specific chunks used to ground it for auditing. Feedback loops are what finally close the system and make it smarter over time. Users interact with the answers they get, providing thumbs up or thumbs down ratings to let you know if the system is working. They might correct a hallucination or ask a follow-up question, and all of those signals flow back to the orchestration layer. High-confidence correct answers are cached to save money later, while failed retrievals are flagged so an engineer can investigate what went wrong. Systematic biases, like certain question types always returning bad results, are surfaced to the engineering teams for a fix. The orchestration layer aggregates all of this feedback and uses it to trigger retraining for the models. Thresholds are adjusted, routing heuristics get better, and query classifiers are retrained on the actual logs of what users asked and what happened. User behavior is essentially teaching the system how to evolve without you having to hardcode every change. Monitoring is the eyes and ears of the entire operation. The orchestration layer instruments every stage with metrics like retrieval precision, answer accuracy, latency, and the cost of every single query. These metrics flow into a dedicated store, and dashboards visualize the health of the system in real time. Alerts fire the moment performance starts to degrade, which allows you to react before users notice a problem. If latency suddenly spikes, you can drill down to see exactly which stage is causing the delay. If precision drops, you can identify which categories of questions are failing and why. If the cost per query starts rising, you can detect which operations became expensive and optimize them. This level of observability allows for rapid diagnosis and prevents the kind of silent failures that kill trust in a system. Scaling happens in two different dimensions to keep up with demand. Horizontal scaling adds raw capacity by spinning up more instances of the retrieval service, more embedding workers, or more re-ranker replicas. Load is distributed across these resources, and the total throughput of the system increases. Vertical scaling is more about optimizing performance, like switching to a smaller, faster embedding model or a more efficient vector database. This makes the system leaner, and latency decreases as a result. The orchestration layer manages all of this scaling by routing traffic only to healthy instances. It can gradually drain capacity from old deployments and move it to new ones without dropping a single request. It monitors how resources are being used and triggers auto-scaling the moment specific thresholds are reached. The system adapts to the demand on its own, and that's the power of orchestration. It isn't just a collection of parts, it's a cohesive system where every part serves the whole. Data flows, queries get answered, and feedback makes the whole thing better over time. The orchestration layer is what makes 3.5 million pages actually useful, because without it, you just have a pile of disconnected pieces. Cost analysis, semantic versus fixed chunking at scale. Budget matters more than people realize, and when you're dealing with 3.5 million pages, the cost difference between chunking strategies is massive. You aren't just paying a one-time fee to set this up, because you're actually paying every single day the system is running. Every page you ingest costs money, and every query a user sends triggers more costs. These expenses compound across millions of operations, and a tiny overhead multiplier that looks small on paper becomes a huge line item in your budget. It all starts with the pre-processing stage. When you chunk 3.5 million pages using fixed recursive chunking, the work is linear and predictable. You tokenize the text, you split it at the boundaries you've set, and you move on to the next page. The computational cost for each page is basically a constant, which means you can parallelize the work across a cluster very easily. 1,000 machines can process 1,000 pages at the same time, and the whole pre-processing job can be finished in a few hours. When you switch to semantic chunking, the work becomes fundamentally different and much more expensive. You can't just split at boundaries anymore, because now you have to compute embeddings for every single sentence. You have to calculate similarity scores between those sentences and detect exactly where those scores drop below a certain threshold. You merge small segments, recompute the embeddings at the segment level, and the whole process requires multiple passes through neural models. A single page might require embedding every sentence individually just to make a decision about where a chunk should end. A cost multiplier of 1.5 to 3 times is actually a conservative estimate for this. Some setups pay even more than that, depending on how sophisticated the logic is. Embedding costs scale directly with the number of chunks you create. Your vector database is going to bill you based on how many vectors you're storing in the index. If semantic chunking produces a lot of small chunks, which it usually does because it breaks things down by topic, you end up with more total chunks from the same content. More chunks means more embeddings to generate, and that leads to higher costs during ingestion and higher storage fees every month. At a scale of 3.5 million pages, even a small increase in the average chunk count has real financial consequences. If semantic chunking increases your chunk count by 20%, you're paying 20% more for your embeddings and your vector storage. That is a material difference that adds up fast. When you multiply that by your model costs and your database subscription tier, the difference becomes very visible to whoever is paying the bills. Storage costs only make this effect worse over time. Vector databases usually charge based on the number of vectors you have stored, and some of them charge per million vectors every month. Regardless of how they price it, more vectors always mean a higher bill at the end of the month. A recursive fixed chunking strategy at 512 tokens might produce 1 million chunks from your data. Semantic chunking might produce 1.2 or even 1.5 million chunks from that same data. Every single one of those extra vectors has to be stored, indexed, and searched. The storage multiplier is direct, so more vectors lead to a higher bill every single time. Query time costs are another factor that people often overlook. When you search a larger index with more candidates, the retrieval process takes longer and uses more compute. Your vector database has to evaluate more distances, and your keyword index has more postings to look through. Your re-ranker also has to evaluate more candidates before it can produce the final rankings for the user. Re-ranking 50 candidates is much cheaper than re-ranking 150 candidates. If semantic chunking creates smaller chunks, you'll have to retrieve more of them just to reconstruct the context for the answer. You end up re-ranking more and passing more data through the system, which makes every query incrementally more expensive. The cost of the LLM context is less obvious, but it's very consequential for your bottom line. Better chunking is supposed to reduce token waste, but it can actually do the opposite if you aren't careful. If your chunks are larger and more coherent, you might only need to pass 3 of them to the LLM to get a good answer. If your chunks are fragmented into tiny pieces, you might have to pass 8 chunks to capture the same amount of information. LLM costs scale with how many tokens you consume in the prompt. 8 chunks of 200 tokens each adds up to 1600 tokens, while 3 chunks of 500 tokens is only 1500. In this case, the semantic chunking scenario uses more tokens to provide the exact same information. These API costs compound across millions of queries, and while the difference isn't a disaster for one query, it's significant for the whole operation. A break-even analysis will show you when semantic chunking actually justifies the extra money. For general document retrieval, the break-even point almost never arrives because the overhead costs are higher than the quality improvements. However, for high-value domains like complex legal documents or regulatory filings, the extra cost can be worth it. When the precision of the answer is worth more than the pre-processing expense, then semantic approaches become a lot easier to defend. For 3.5 million pages of mixed content, you might apply semantic chunking to the top 10% of your most important files. This hybrid approach gives you the precision where it matters most while keeping costs down across the rest of the corpus. The lesson here is to be pragmatic with your budget. Start with fixed recursive chunking and measure exactly what you're spending. You should only invest in semantic refinement when you can prove that the gain in precision is worth the extra expense. Governance and compliance at scale. When you are managing 3.5 million pages, governance isn't just a nice feature to have, it is the absolute foundation of the system. The retrieval tools might work and the AI might generate great answers, but without governance, you are leaving yourself wide open to massive exposure. At this kind of volume, a single policy mistake can leak thousands of sensitive documents, and a missed legal hold can literally destroy evidence needed for court. Governance is the only thing that stops these small errors from turning into total system failures. Data classification has to start long before the retrieval process even begins. Every single document that enters your system gets sorted into a specific tier, ranging from public and internal to confidential or restricted. Public files can be shared with anyone and kept forever, while internal documents are strictly for the organization and can never be shared outside the company. Confidential files require a specific need-to-know clearance, and restricted documents are tied to legal holds or regulations that require very specific handling rules. This classification isn't just a label for show because it actually dictates how the entire system behaves. If a document is marked restricted, the system won't let you delete it without legal sign-off, and confidential files won't even show up in a search unless the user has been granted explicit access. Retention policies are what define the lifecycle of your data. You have to decide how long a document stays in your active index, which might be years for a legal case or just 3 years for a standard business memo. Certain industries have strict mandates like keeping financial records for 7 years or employment files for 5, but retention isn't just about hitting a delete button. It is about transitions where active documents stay in fast access tiers, while older files move to cheaper, slower storage with reduced searchability. Your policies encode this entire journey, so when a document hits its expiration date, the system moves it automatically. Users can't find these archived files through a normal Copilot search, and getting to them requires special permission and a full audit trail. Legal holds will always override your standard retention rules. During a lawsuit or an investigation, certain documents become immutable, meaning they cannot be moved, changed, or deleted, no matter what the original policy said. Once the legal department issues a hold, the system tags those files, and they stay frozen even if they were scheduled for deletion that very day. Normal retention only starts back up once the hold is officially lifted. If you don't have this logic built in, you run the risk of destroying evidence during a routine cleanup. But a good system lets litigation needs and daily compliance live together without any conflict. Audit logging is how you record every single thing that happens. Every time a user asks a question, the system logs who made the request, which documents were pulled, and whether the user actually opened them or just saw them in a summary. Every AI response is tracked to show which documents were used as context and if the answer cited them correctly. We also log every change in classification and every time access is granted or denied, but these logs aren't there to help with speed or performance. They exist for accountability, giving you a clear timeline if a breach happens or if a regulator asks how you handled specific data. These logs are permanent and cannot be deleted by users, and we actually keep them longer than the source documents to prove we stayed compliant. Data residency is how you manage the geography of your information. Regulations in the EU require personal data to stay within their borders, just like US health data and various financial records have their own strict jurisdictional rules. Your retrieval system has to respect these lines, so if a US user tries to process EU data, the system won't pull from a US index. Instead, the orchestration layer transparently routes that request to a compliant region in Europe. Because every document has residency tags built into its classification, the routing happens automatically without the user ever needing to think about it. Incident response is your way of catching a breach before it spreads. If a user suddenly tries to pull thousands of documents they've never looked at before, the system triggers an immediate alert. We also have detection tools that watch for sensitive data appearing in answers where it shouldn't be, or for users logging in from unexpected regions to access restricted files. These detection systems feed directly into response workflows, so your security team can investigate and fix the problem. Once the issue is resolved, we go back and adjust the preventive policies to make sure it doesn't happen again. When governance is working the way it should, it stays completely invisible to the end user. The people using the system just see the answers they need, while the backend quietly makes sure those answers follow the law, respect retention dates, and keep a perfect audit trail. The goal is a system that doesn't just fail silently when a policy is broken, but instead escalates the issue so it can be handled properly. Real-world implementation, the workflow. Theory is great for planning, but you need to know how this actually looks when you put it into practice. When you are standing up a system to manage 3.5 million pages, you have to follow a very specific execution plan. The timeline is vital because every phase is designed to prove your architecture works before you try to scale it up to the full corpus. Day one is all about ingestion and extraction. You start with a massive data dump of 3.5 million pages, including everything from PDFs and emails to old scanned images and video files. The ingestion pipeline starts moving immediately, and we run the extraction process at the same time to break those files down. PDF parsers pull out the text, OCR technology turns scanned images into readable data, and we catalog all the metadata for every video and image file. We aren't looking for perfection on the first day, so it is fine if the OCR misses a few characters or a parser mislabels a section. The goal is to get coverage across the entire dataset, while a background process identifies names, dates, and organizations. By the time the sun goes down on day one, you have a raw version of your content registered in the system and ready for the next step. Days 2 through 7 are dedicated to indexing. All that extracted content goes through a chunking process that respects the natural hierarchy of the documents, and we tag those chunks with the entities and sensitivity levels we found earlier. The system starts filling up the Tier 1 and Tier 2 indexes, giving high-value files like legal filings, full semantic indexing with vector embeddings. At the same time, the knowledge graph starts building connections between people and dates, while less important content goes into keyword-based storage. You don't have to wait for the whole thing to finish to start testing, so you can run sample queries to see if you can find documents by name or topic. These early tests tell you if your chunking is working and if the system is respecting the structure of your data. Week 2 is when you finally deploy your agents. The Agentic router is the brain of the system that understands what a user wants and breaks their query down into smaller parts. This is the moment where your design meets the real world, and you start feeding the system complex questions like asking for all emails between two specific people from the year 2005. The router has to classify that request, generate subqueries, and pull data from both the knowledge graph and the document index. Once the results come back, the router merges them into a single answer, and you have to manually check if that answer is actually right. This phase usually reveals where your assumptions were wrong, like a query going to the wrong index, which allows you to iterate and fix the biggest problems before moving on. Week 3 is when you turn on re-ranking. We bring the cross-encoder model online to sharpen the precision of the results, but you have to keep a close eye on how much this slows things down. If your basic search took 30 milliseconds and re-ranking bumps it up to 150, you have to decide if that extra time is worth it. In most cases, a 40% jump in precision is a fair trade for an extra 120 milliseconds of wait time. If the delay is too long for your users, you can always shrink the number of documents you are re-ranking or switch to a smaller, faster model. Week 4 is the pilot rollout. You don't give the system to everyone at once, but instead you hand it to a small group like the legal team who really knows the data. They start running real-world queries and giving you feedback, hitting a thumbs up for good answers and correcting the system when it misses the mark. This feedback goes straight into your monitoring tools so you can see exactly where the system is struggling. You might find that time-based questions work perfectly while relationship queries are missing some connections, but you don't rush to change things yet. You take the time to observe and understand these failure patterns before you start tweaking the settings. Ongoing operations are all about constant monitoring and small adjustments. You have to track your latency metrics every day, because if the system starts slowing down, you need to know if the index is getting too big or if the cache isn't working. We also keep a close eye on the cost per query to make sure a new feature hasn't made the system inefficient. Quality is measured against a set of gold standard questions, so if the precision starts to slip, you know exactly which part of the retrieval or ranking process needs work. The system evolves slowly, getting better with every interaction and every correction until it becomes a truly reliable tool. Common failure modes and how to avoid them. Even with a solid architecture, things can break, and usually they break in predictable ways. Overfragmentation is a silent killer for usability. When you create chunks that are too small, say under 200 tokens, you force the retrieval system to pull dozens of fragments just to reconstruct one coherent thought. Imagine a legal deposition that spans 300 tokens but gets split into 4 separate chunks. If a user asks a question that matches only the second chunk, the system retrieves it, but the context is gone. The witness statement leading up to that testimony is sitting in a different chunk, and the follow-up question is in another one entirely. What the LLM receives is a fragmented mosaic instead of a continuous narrative, which leads it to hallucinate connections or miss the nuance of the conversation. Users will notice that the answers feel scattered and incomplete. On the other hand, chunks that are too large create massive amounts of retrieval noise. A 5,000 token chunk covering an entire legal section might contain a few core facts mixed with pages of tangential discussion. When this gets retrieved, it swamps the context window with irrelevant details, and the LLM struggles to find the needle in the haystack. Both of these extremes will break your downstream performance. The only way to prevent this is through constant measurement. You need to monitor your chunk size distribution and calculate exactly what percentage of your data falls below 200 tokens or exceeds 2,000. When you see the distribution skewing toward these extremes, you have to adjust the minimum and maximum bounds. The goal isn't to make every chunk identical, but you need enough consistency to prevent these pathological cases from ruining the user experience. Permission misalignment is a much more dangerous problem because it's a silent security breach. You might build a robust retrieval system, but if the permission metadata attached to your chunks becomes stale, you have a major liability. Consider a situation where a user changes teams and their access profile is updated in your identity system. If the retrieval system hasn't revalidated those permissions against the updated identity, the system is flying blind. The user runs a query, and the retrieval engine returns a chunk they no longer have the right to see. Because the permission check ran against cached, outdated credentials, the restricted information passes through without being filtered. This is actually worse than a total system failure because it isn't visible to the admins. To prevent this, you need a strict synchronization discipline where permission metadata is refreshed on a regular schedule. Depending on how often people move roles in your company, this should happen daily or even weekly. When access policies change in your primary identity system, those changes must flow to the retrieval cache immediately. You should never rely on cached permissions for more than a few hours at a time. It's also vital to test these boundaries continuously by running synthetic queries as a restricted user. You need to verify that those restricted chunks are actually being filtered out in real time. Don't just assume the permission system is working. You have to validate it. Stale metadata causes your system to drift away from reality over time. During the initial ingestion, your enrichment pipelines extract dates, assign classifications, and map out relationships between entities. But documents are living things that evolve. A file might change from confidential to internal, or a document might be superseded by a newer version without the old one being deleted. Sometimes a legal hold expires, but nobody remembers to update the metadata tags. These small errors accumulate until your retrieval system is operating on a mountain of outdated information. Users start seeing results ordered by the wrong dates, and classifications no longer match current company policy. Because this degradation happens gradually, it's easy to miss until the system is significantly compromised. The fix is a scheduled refreshment of your data. Major fields like classification, retention status, and legal hold states need to be revalidated periodically. At least once a quarter, you should scan the entire corpus and compare the metadata against your current policies. When you find a mismatch, you update it. For high-velocity fields that change frequently, you'll need to increase that frequency, while quarterly checks are usually enough for stable fields like document types. You should also set up automated alerts for any document whose metadata hasn't been touched in longer than expected. Routing errors are another common pitfall where queries get sent to the wrong specialized systems. This happens when the intent classifier misses the signals in a user's question. For example, a query about complex financial relationships might get routed to a standard document search instead of a graph database. As a result, the answer misses all the structured relationship data it needs, or perhaps a temporal query gets sent to a keyword search instead of a time-indexed system, leading to results from the wrong years. These failures often go unnoticed because the system still returns results, they just aren't the right ones. To stop this, you need a continuous validation loop. You should maintain a dedicated test set of queries where the correct routing is already known, and you should run these tests every single day. If the routing classifications start to shift, you need to investigate why. If certain types of questions are consistently failing, it's time to retrain your classifier. You should also monitor routing decisions alongside the actual retrieval outcomes. When you see that queries matching a specific pattern are consistently producing poor results, it's a clear sign that your routing logic is broken. Re-ranking collapse occurs when your model becomes miscalibrated. If you have an aggressive re-ranker, it might assign incredibly low scores to perfectly legitimate candidates, leaving your top results empty. Conversely, a conservative re-ranker might barely change the order of the initial results at all. In that case, the re-ranking process is just adding latency to the system without actually improving the precision of the answers. You prevent this through empirical tuning. You have to test the re-ranker against a sample of real queries and measure exactly how much it's changing the order of the results. You need to validate that these changes are actually making the answers more accurate. If the re-ranker is moving things around for no reason or having almost no impact, you need to adjust your thresholds or change the size of your candidate set. Finally, there is the issue of latency creep, which comes from a dozen small optimizations piling up. Each new feature might only add 10 milliseconds, but then the re-ranker adds 150 and the permission checks add another 30. Before you know it, the total latency has climbed to 300 milliseconds. Then someone adds query expansion or extra caching overhead, and suddenly the system feels sluggish. You have to be ruthless about monitoring these numbers. Every single component in your pipeline should report its own latency, and you need dashboards that show the cumulative total. When that total hits your budget ceiling, you have to make a choice. If you want to add a new feature, you have to find a way to remove or optimize an old one to keep the system responsive. Monitoring, evaluation, and continuous improvement. The reality is that you cannot optimize what you aren't measuring, and this is exactly where most RAG implementations fall apart. The system might be running and users might be getting answers, but without proper instrumentation, you are flying blind. You won't know if the precision is slowly drifting downward or if a recent update made the latency unbearable for your users. You won't even know if your cost per query is starting to spike. Measurement is the only thing that stands between a system that degrades in the dark and one that actually gets better over time. Retrieval metrics are your first line of defense because they tell you if the pipeline is finding the right candidates. You should be looking at precision at K, which measures how many of your top retrieved results are actually relevant. If you pull the top 50 candidates but only 35 of them matter, your precision is sitting at 70%. You also need to track recall at K to see if you're capturing all the relevant documents available in the corpus. If there are 100 matching documents but you only find 40 of them, your recall is failing. These metrics help you diagnose the specific flavor of your quality issues. You might have high recall but low precision, meaning you're finding the right info but drowning it in noise. Or you might have the opposite problem, where what you find is accurate but you're missing the bigger picture. You should also use NDCG to measure the quality of your ranking. A relevant document that shows up in the first slot is much more valuable than one buried at number 50, and NDCG captures that difference. Mean reciprocal rank is another useful tool that tells you how far down the list a user has to go to find their first real answer. These aren't just academic numbers. They correlate directly with how happy your users are. When precision is high, users don't have to deal with false leads. When recall is high, they don't miss critical evidence. The quality of your ranking is what determines if the system feels like a shortcut or a chore. Answer quality metrics are what your users actually care about at the end of the day. You need to measure faithfulness, which asks if the answer stays true to the source documents. An unfaithful answer is one that contradicts the evidence or starts guessing. Then there is relevance, which checks if the system actually answered the specific question the user asked. You also need to look at grounding. Can every single factual claim in the response be traced back to a specific source chunk? Citation accuracy is just as important because you need to know if the links actually support the claims they're attached to. Since these are qualitative metrics, you can't just calculate them with a simple algorithm. They require human judgment or expert review. The best approach is to build a gold standard evaluation set of about 500 representative questions with verified answers and citations. You run your system against this set and have experts score the results. By tracking these scores over time, you can see exactly when a change in the pipeline helps or hurts the final output. Latency metrics need to be broken down by every single component in the chain. You should track the time to the first byte so you know when the user first sees text on their screen. You need to measure the time from the initial query to the moment retrieval is finished, and then the time from retrieval to the first LLM token. It's important to remember that percentile latency matters much more than the average. Your average response time might look great at 200 milliseconds, but if your P99 is 5 seconds, 1% of your users are having a terrible experience. You should track PFD, P95, and P99 latencies religiously. When the P99 starts to lag, you need to find out why. Is a specific type of query slow? Is one of your subsystems hitting a resource limit? Percentiles will show you the failures that averages hide. Cost metrics are how you track the actual business impact of the system. You should calculate the cost per query by dividing your total infrastructure spend by the number of queries you serve. If you're spending $50,000 a month to serve 1 million queries, you're looking at 5 cents per query. But an even better metric is the cost per successful answer. Not every query produces a good result, and only the successful ones actually provide value. This metric tells you if your system is becoming more efficient over time. You should also break down your infrastructure costs by component, looking at retrieval, re-ranking, LLM tokens, and storage. If the total cost starts to climb, you can drill down to see if the LLM is consuming too many tokens or if your storage costs are scaling poorly. User feedback is the final piece of the puzzle that closes the loop. Simple thumbs up or down ratings can tell you if the answers were useful in the real world. You can also look at escalation rates to see how often users have to give up and ask a human for help. When those rates go up, it's a clear signal that the system is hitting a wall. You should make it as easy as possible for users to provide this feedback directly in the interface. When users rate thousands of answers, that data becomes a goldmine for future improvements. Finally, you need to move toward automated offline evaluation. Instead of checking things manually, your system should run a benchmark set of questions against your live indexes every single night. It should compute precision, recall, and NDCG automatically and compare them to your baseline. This allows you to detect regressions before a single user ever sees them. This kind of discipline is what separates a project that slowly falls apart from a professional system that catches problems and fixes them before they become disasters. Future directions beyond 3.5 million pages. The Epstein files case shows us what happens when you build with intention at a massive scale. But here's the problem. The architecture you build today is just the foundation for tomorrow's headaches. Those constraints that drove our design, the 3.5 million pages, the messy multimodal files, the strict permissions, those aren't going to stay the same. Data grows, requirements shift, new tech shows up. It is not a question of if your system needs to change, but how you plan for that change right now. Agentic workflows are the next step in this journey. Up until now, retrieval has been a simple operation. You ask a question, the system finds some text, the model reads it and gives you an answer. But sophisticated users don't actually want answers. They want reasoning. They want to compare a witness's testimony across 3 different depositions to find where they lied. That isn't just finding text and repeating it. That is a process of finding, synthesizing, comparing, and judging. An agentic system treats every one of those steps as its own job. The agent pulls the first deposition. Then it pulls the second and third. It runs them through a specific tool designed to find contradictions. It thinks about what that means for the witness's credibility. This requires agents that can use multiple tools in a row, check their own work, and decide what to do next. Current systems do this a little bit, but in the future, this kind of reasoning will be the default. You need to build your architecture today so that retrieval is a tool an agent can call rather than a closed box that nobody can touch. We are also seeing a shift toward graph-based RAG. This moves us away from simple math-based similarity and toward actual relationships. Your knowledge graph today maps people and how they are connected. Tomorrow, that graph becomes the main way you find information. Instead of looking for similar words, the system treats your question like a map. If you ask what transactions connected person X to organization Y between 2005 and 2007, that isn't a text search, it is a graph traversal. The system starts at the person, follows the money trails, filters by the dates, and shows you the path. This means you have to start investing in graph infrastructure like property graphs and relationship engines right now. This doesn't mean we stop using vector search. It means we use both. If your data is all about relationships, you use the graph. If it is all about heavy text, you use vectors. The system just learns how to route the question to the right place. Streaming retrieval is going to change how users actually feel the system working. Right now, you ask a question and you wait. The system finds the data, ranks it, builds the context, and finally shows you an answer. You see the whole thing at once after a long pause. Streaming flips that logic. Results start appearing as they are found. The system shows you the best guess immediately, while it keeps looking for better evidence in the background. The model starts talking to you based on the first piece of evidence, while the retrieval engine is still working to find something even better. This means we have to stop thinking of this as a straight line where one thing happens after another. We have to decouple finding data from talking about it. Even if the total time is the same, the user feels like the system is faster because they aren't staring at a loading spinner. Then there is personalization. Today, everyone gets the same answer to the same question. Tomorrow, the system will look at who you are and what you do. If an executive asks about transactions from 2005, they get a high-level summary. If a forensic analyst asks that same question, they get the raw evidence and the full citations. This isn't about changing the facts. It is about changing the priority. If you care about dates, the system shows you a timeline. If you care about networks, it shows you a map. The results stay grounded in reality, but the way they are served to you fits your job. We are also moving toward cross-silo orchestration. As these systems grow, you'll need to look outside your own walls. You might need to check partner data, government records, or public files. One layer will coordinate all of that, even though every source has its own security and its own rules. The system will negotiate those permissions for you. It will respect the rules of each silo and then merge the results into one coherent thought. Finally, we have sovereign AI. Regulations are getting tighter every day. You have to be able to prove that your data stays where it belongs, whether that is the EU or a specific industry. Sovereign systems will route your questions only to approved hardware and models. This prevents data from leaking across borders. This isn't a maybe for the future. If you are building a global system today, you need to build sovereignty into the core. Key takeaways for enterprise leaders. If you are the one in charge of rolling out Copilot, the choices you make right now will decide if it works or fails. These aren't just IT tickets. These are business decisions that carry real risks and real costs. The first thing to realize is that scale changes everything. If you have 10,000 pages, the standard approach works fine. You just index it all and call it a day. But 3.5 million pages will break that model every single time. The money doesn't make sense. The speed drops. The noise gets too loud. At this scale, you stop asking if you can index something. You start asking if that data is actually worth the cost of making it smart. That is a massive shift in how you think. It means you have to prioritize. A leader who gets this will spend their budget wisely. A leader who doesn't will go broke trying to index junk. Governance is not a nice-to-have feature. It is the foundation of the whole building. Sometimes people try to bolt security on at the end of a project. At this scale, that is impossible. Your permission model is what makes the system work. It is what keeps your data safe. Your audit trails are the only thing standing between you and a massive fine. You have to build governance in from the very first day. Yes, it adds some complexity and a little bit of lag, but paying that price now is much cheaper than trying to fix a data breach later. Selective activation is a strategy, not a failure. Not all of your data is equally important. Your legal filings and key depositions deserve the best indexing and the most expensive processing. Your old background files and supporting documents can live in a cheaper, lighter index. Your archives can stay in cold storage until they are needed. This kind of tiering is how you survive at scale without an unlimited budget. It is the difference between hoping your system can grow and knowing it will. You also have to measure everything. You cannot fix what you aren't tracking. This means you need metrics from the moment you turn the system on. You need to know the cost per query and the accuracy of the answers. You need to hear what the users actually think. Set your baselines before you go live so you can see when things start to drift. The teams that measure their progress are the ones that succeed. The ones that don't just wander into bad performance without even knowing why. There is always a trade-off between speed and cost. If you want better accuracy, you might add a re-ranking step, but that adds 150 milliseconds to the wait. If you want better security, you add permission filters, but that adds overhead. Every single improvement has a price tag attached to it. The question is whether that improvement is worth it for your specific case. A basic chatbot needs to be fast, so you might skip the extra steps. A legal tool needs to be perfect, so you pay the price for precision. You have to make these choices on purpose. Lastly, a phased rollout is just good risk management. It isn't a delay. Start with the low-risk areas and the users who understand that the tech isn't perfect yet. Listen to their feedback. That feedback will tell you what is actually happening in the real world before you try to scale to the whole company. It is much cheaper to fix a mistake for 100 people than it is for 1 million. If you rush the deployment, you will hit a wall. If you move deliberately, you can fix the problems while they are still small and then scale with total confidence. The Epstein files case proves that running Copilot at a massive scale isn't just about finding data. It's about orchestration. The system only works because every single part has a specific coordinated job to do. Selective activation focuses on the data that actually matters, while structure-aware chunking keeps the original meaning of the documents intact. Agentic routing figures out what the user actually wants, and hybrid retrieval pulls that signal out from millions of pages. This entire choreography, including permission-aware security and constant monitoring for drift, is the only reason 3.5 million pages stay searchable. The old way of thinking doesn't work anymore. If you treat this like a simple data problem, you're going to fail. Success comes when you treat it as an architecture problem instead. The real difference here isn't how complex the tools are, but how intentional you are with the design. If these principles changed how you think about building at scale, leave a review for the M365 FM podcast. It helps more people find these insights on Microsoft 365 and the modern workplace. Follow me, Mirko Peters, on LinkedIn and share the challenges you're facing right now. We'll figure out the next generation of enterprise AI together.